Okay, then let's start. Thanks for coming today. Frontier material for Young Scientists Symposium in Korean Vacuum Society. It's really great to have this nice symposium here. Today's keynote speaker is Professor Luke Lee in Harvard Medical School. He's professor of medicine in Harvard Medical School and also a founding director of the Institute of Quantum Biophysics in Samkyungwan University. So his talk is about the toward quantum biological integrated circuits for life. Okay, so Professor Lee, go ahead.
Okay, let me just connect this. Just a second. Okay, can you hear me?
Yes, you hear.
Right. Thank you for your kind introduction. Today, I'll talk about our kind of progress. So I named it, this title as a toward quantum biological integrated circuit, QBICS, for life science and medicine. At the end, I'll talk about importance of this quantum biological circuit or electron tunneling. But at the beginning, I'll talk about how we felt that it is necessary. So I'll share some of the research, our previous research. Bear with me that the quantum biological aspect will come at the end or in the middle. But first of all, thank you. I'm really thankful for a lot of my students and postdocs, as well as visiting scholars and collaborators and undergraduate students to really develop new technology and science. And also thankful for many research funding agents like NIH, NSF, DARPA, and NASA, and so on. It's great. Group, we are writing the healthy poem because we want to get inspiration from photonics, from nature, and then develop optofluidics, electronic technology, and science. So our goal is patient-oriented engineering medicine, so that we can think about how to develop many different integrated optical or microfluidic circuit with the photonic applications. But I'd like to share with you a real poem, not the technical poem that we are writing on the chip. This 4-line by William Blake really summarized my research. So I'll explain to you each line, how to see a world in the grain of sand, and a heaven in the wildflower, and whole infinity in the palm of your hand, and eternity in an hour. Let me just show you. First line, to see a world in the grain of sand.
To see the world in a grain of sand. Is it possible to gaze at the health status of humanity and the earth in a grain of sand? Can we create smart sands to view DNA and RNA fingerprints from our blood and the earth in real time? Reflecting on Blake's poem in our fast-paced world provides an inspiration to find a proactive solution for our global biosecurity. The world is more dangerous today due to the emergence and spread of new infectious diseases. We can prevent such outbreaks from happening through early detection. We propose SANDS, Speedy Analytical Nano-Optofluidic Diagnostic Systems. Smart SANDS are on-chip for rapid and accurate molecular diagnostics. Smart SANDS can be used by anyone with a smartphone, even in areas where rapid and accurate diagnostics are usually inaccessible. Smart SANDS fully connected SAN's rapid molecular diagnostic network for human, agricultural, and environmental health will improve global healthcare and empower us to create a new, proactive, predictive, and preventative paradigm for enhancing global biosecurity. Is it possible to gaze at the health status of humanity and the earth in a grain of sand?
This was the vision, and we proposed this to the Singapore government. So this is already 10 years old vision. If we had this like before COVID-19, we probably had a better way to protect. Unfortunately, due to the politics, how to execute this mission. Oops. So I hope you got the idea to see world's health in a grain of the smart sand. The reason why I'm saying that this smart sand, it's not just because of the poem, but it's because in Silicon Valley, where I used to work at UC Berkeley, there are many silicon-based circuit that many people take advantage of it to make industry. So that's why we call it Silicon Valley. But over there, not only making circuit, but also we'll demonstrate first a miniaturized microscope and all insect eyes and so on. So we can really combine this know-how and then think about how to capture molecular information, speedy analytical network. Smart sand is the basically integrated molecular diagnostic system called IMDX for global health. The emphasis is sample to answer device at low cost. So we really want to make sure that it is assured smart sand to those people who really need to test without any other extra tool or equipment. So we have to make it affordable and sensitive and specific and user-friendly and robust or equipment-free deliverable system. So this is history. 2008, like early 2000, we developed many different microfluidic devices, but this is the first integrated NASBA. NASBA is one of the isotomal amplification, the method. So we developed RT NASBA on a chip step, and then we developed the SIMBAS, which is a cell-powered integrated microfluidic blood analysis system that allowed to separate plasma only out of the blood, so that you can basically do immunoassay or PCR. And then we developed in 2011 sepsis diagnostic by PCR. And then 2013 we developed handheld point that can also demonstrate a very simple way of doing isotomal amplification and transmission of the signal and so on. So the idea is using the loop-mediated isotomal amplification method called LAMP. We can demonstrate a very fast genomic diagnostic. As you can see, this is the data. You can really take advantage of this integrated chip with excitation of the light source and heater, so that you can get nice lamp, the signal for HIV diagnostics. And then we also developed on the Rotro-based microfluidic device. This is done with VTT in Finland, and I went there, spent some time to develop the viral RNA detection by LAMP using Rotro fabrication. So using Rotro fabrication, we can also accomplish the LAMP on the chip that I mentioned to you previously. So advantage with Rotro is massive manufacturing at low cost. That's the reason we use the Rotro fabrication method. And then 2017, using the Bill Gates Foundation grant, we made a simple chip for infectious disease identification. So it's a self-power and integrated microfluidic point of care, low-cost enabling molecular diagnostic system. As you can see, this chip, this is inlet, and there's a small wells that has a reaction chamber, and this is the vacuum battery. I'll explain to you soon. So here, in order to reduce every step, we integrate amplification initiator inside. We pattern this so that as soon as we separate the plasma from the blood, and the plasma will react with the amplification initiator in this chamber. But this chamber is a vacuum, bubble free, because there is a vacuum battery that you nice suction so that you will avoid any the bubble formations. So this is the movie file showing that how this operates. There's no external pump. This is a vacuum battery here. It's a mechanical battery. It's not an electrical battery, as you can see. And this allowed to make a nice suction because we store this negative pressure so that you can pump and then isolate this individual chamber to be the reactor of the nucleic acid amplification. So we call it this as a digital plasma separation unit. And then we can show you the animation that's showing that how we can pull or push all the cell and then trap, all the plasma. And this is the case with the wrong design. I just want to show you that we have to improve this design so that you can make a 95% plasma separation. This is you can see this is isolated example, and then blood cell can be separated so that you can have a nice plasma in each well. So plasma from body the mRNA or HIV RNA, just like a COVID RNA, this is the same concept. It's almost identical, except it's a different virus, but whether our mRNA or COVID or HIV, we can basically do same application. It's showing you that we can detect definitely 10 to the 5th copy per microliter, 4th, 3rd, and 2nd, or even 10 copy. 100 or 10 copy. So we can really accomplish this sample prep. There's no sample prep step here. You have to walk through all the pipe. So we want to continue to prove. We want to also not only DNA and RNA and protein detection on one chip, because we have to see not only the specific the infectious disease, but also need to see whether you have an immune system or not. When you the COVID-19 vaccine, you have to think about when does it disappear. Really to see antibody reaction. I want to share with you saying that this is the first FDA authorized, first approved system. COVID-19 happened last year. This is from our group. Students made first LAMP-based. The one I just described you a few minutes ago is the LAMP-based, the FDA home diagnostic system. Now, next one, I want to talk about nanoscale SAN, whether we can really see cellular galaxy. This is image is like a star, but actually this is the nanoparticle, a nanoplasmonic particle inside of the cell. Different color means different material and shape. So asking question, is it really possible to see electron transfer in living cell with the grain of the sand, with this tiny, tiny nanoparticle? So we need to think about how to explore living cell to really capture electron transfer information using nanoscale satellite. Oops. So we've been developing nanoscale sand, the biological optical antenna. So it's a different shape, and in this case, crescent shape, and this is a different, and this is case with one side is half side is plasmonic, half side is polymer to attach specific antibody. And this is using virus, actually plant virus. Plant virus has a beautiful nanostructure, but it's not harmful for humans. So we take advantage of this plant virus topology. Or we make also magnetic layer inside of this crescent so that we can move them around inside of the cell. Or on a rod, so that you can make a circuit model like this. But then we monitor electron transfer dynamic in living cell. So using this nanoscale sand, we can monitor and then see the regulation, or we can modulate and understand electron transfer so that if there is an issue with mitochondria or there is a problem with the energy, we can think about how to deliver new physical drug instead of using chemical drug. So you got motion, electronic state of the molecule or vibrational state of the molecule. So the basic concept we are using is this fluorescent. When you shine the light, basically you can oscillate electron in the surface so that you can make a coherent charge oscillation in this metal surface in between metal and dielectric layers so that you can make a charge oscillation. And this is a really nice, simple way to really generate a different wave by knowing permittivity of the metal and medium, and so that you can take advantage of nice nanoplasmonic optics that you can focus in nanoscale. Even though you are using red or visible, you can focus down to the particle size. If particle is 100 nanometer or if 50 nanometer, you are focusing this light into this small particle so that you can take advantage of nice precision temperature control or precision the quantum electron transfer measurement and so on. So this nanocrescent as a smart nanoscale sand, you can take advantage of the activation in biological circuit. When I say biological circuit, real biological on and off for the gene circuit, so that we can take advantage of the precision life science or therapeutic. Just like the current vaccine using mRNA, you have to think about how to turn on every time instead of just turning on all the time as soon as we receive vaccine. Also, we can take advantage of the foreign reaction or reactions, or we can make amplification of the biological reaction using this kind of structure. So you can take advantage of many optical as well as a therapeutic and precision life science control. And it's very interesting to watch this Kandinsky's drawing. I accidentally found this, but this is similar to this nanocrescent, right? But a long time before I was born, Kandinsky drew this, and he was thinking about associating this shape and color with a musical note and rhythm. I look at this shape and material, but I look at this different shape and material with optical resonance and color to control. So whenever you need to take off from heavy duty science, and you can enjoy watching art and then connect with the different. So if you use a specific wavelengths to specific size or specific material, you can generate excitation of the electron, and then you can emit the to the oscillation of electron. So you connect surface plasma excitation state, and then connect it with the. You can think about how this simple the gold particle can be used as a biological optical antenna. Then we can attach the ion channel, and then you open those, or you can attach to this antibody that you can re-specify, like the COVID protein, you can detect with this kind of plasmonic, or you can attach the RNA in this case, then deliver inside, and then liberate this specific gene as specific. So you can take advantage of this nanoplasmonic optical antenna to drug. This means here drug is basically a gene, because you can turn on specific RNA. You cannot control, you have to release all the time. So you can take advantage of also mRNA detection, or you can attach to mitochondria to really read out the electron transfer, or you can read out in the surface enhanced through the surface enhanced Raman scattering and so on. So this is one way that I'm just specifically showing that you can attach gene and deliver by endocytosis, and then use very small light. Instead of using high density laser, you use a LED to liberate using small photon to make a photothermal effect to liberate, attach the gene. So this is the one of simplest way to control in vivo gene delivery. But it's very interesting also, this Kandinsky also make a small and then small circle inside, and as if he was reading my mind a long time ago, because we want to also deliver this crescent, different crescent, which has a different resonance frequency due to the shape. Then you can liberate them at different, also selectively with this different wavelengths. And then you can use it as optical antenna. So I'll just quickly go over that we can make quantum photonic gene circuit by liberating gene. You attach the different gene which has a different resonant frequency or resonant wavelengths to liberate at specific time to block specific mRNA 1 or 2, depends on the different gene, which is attached to different antenna with a different resonant frequency. And then basically you can use this to make a like Boolean algebra. To do the time, I'll to simplify this, but you can attach sRNA to block IKB or P65. So you can control gene expression. Basically, the liberation of the sRNA for IKB or P65 different time. So you can make a Boolean algebra on and off, on for red, turn on for gene for blue, and you can pause instead of the early gene expression and later gene expression, and simultaneously we can intentionally select early expression only. Basically, we can photon you generate gene circuit with big gene delivery at specific time. So spatial temporal control of in vivo gene delivery can be done. So that's what we demonstrated already 10 years ago. Now, let me talk about quantum biological tunneling. Here is it really possible to see the quantum tunneling in living system and then find a solution for eigenvalue problems? So whether you believe or not, quantum biology is happening in our respiration system, olfactory receptor system, as well as the DNA in repairing or damaging or repairing, or a photosynthesis system, or even avian quantum compass, or cryptochrome, and so on. So to the time we cannot really explain everything, but there are many scientists in the world working on quantum biology. I want to introduce something that I get inspiration, or at the same time, I was also questioning whether we have to debunk this textbooks information that you learn in the textbook from the high school, that this photosynthesis system, you use the sunlight and then you excite the photosystem too, and then electron is flowing in the cell membrane. Did anybody measure this electron transfer in the cell membrane? Is it possible to measure electron transfer in cell membrane? Asking your student, this is in your textbook and you believe and you memorize. Is it possible to see and measure that when you shine the photon sunlight, this protein too can excite the electron, and this excited electron is flowing down to photosystem 1. There is a drawing. This number 4 is electron transfer. Is it possible to measure this experimentally? Anybody say yes or no? I guess students are very quiet, but I want you to practice how to speak out. It's in the textbook, but there is no evidence, I couldn't find any literature. I couldn't find any paper that shows electron transfer. Then how can you believe if there is no experimental result? How can we assume that this is true? Is it true or not? In order to prove, we have to do something step by step. But however, a good story, but we have to prove experimentally. So we decide to try at least one side, whether there is any electron tunneling from protein or inorganic to protein. So we'll do protein to protein tunneling experiment in terms of the electron from one electron protein to another protein. We have to think whether there is a possible connection. So we use a plasmonic particle, and if some protein is in the vicinity, you can think about light, and this is the case with the absorption spectrum. But can we really capture this information? Unless you kill the cell and purify the protein, you cannot really capture real-time image of this electronic state information. So we have to think about a new way. So we call it quantum plasmonic resonant energy transfer. So I'll explain this detail again, but in general, you get this scattering, but we want to capture this absorption peak. But if this protein is in the vicinity on top of this, the plasmonic structure, you can get quantized quenching dip. The specific dip is not a general dip. So you can really identify this peak. Let me explain more step by step. So compared to the frat, a beautiful way really give you any spectroscopic information of this, acceptor or donor, give you just fluorescent peak. But as I mentioned, plasma resonant energy transfer, you see specific peak, the wavelengths that you can identify as a specific, the fingerprint information of the molecule. So let me explain step by step. When you shine the plasmonic, and in general, you get a scattering light. But however, if you link with the linker molecule, and then this is a protein, in this case, a cytochrome C enzyme, and then if you shine, you can show that there's electron tunneling. There's a barrier. The barrier thickness depends on this length of this linker molecule, but we want to show that electron is really flowing through this. So we can show by looking at this, the light using spectroscopy, we can capture electronic state absorption peak by looking at this quenching dip, which is identical to this conventional electronic state absorption peak that you can get the purified, the pins. So in order to capture many different information, you have to overlap with the specific antenna. If you have the protein with the absorption peak, and then you can use specific window, the boundary of this window. If you have this antenna, but if there's no the electronic state absorption peak, then you cannot get any signal. But this area is the antenna that will cover with this window, so that you can capture specific effects of this quantum biological electron tunneling. Then what we do with this, so we can use this kind of tool to inside of the cell and then observe electron transfer in the mitochondria. So this is the cell, and all this dot is scattering light, and you cannot see this the spectrum by looking at it with the eyes, but you can use a spectroscopy, so we can really make nice tunneling distance measurement this different linker molecule. You can use carboxyl terminated alkyl linker or aromatic linker with a different distance. This you can see with different distance get different electron tunneling measurement. You can using plasmonic resonance, so you can take advantage of plasmon-induced electron tunneling with also aromatic ring that due to this sp orbital that there is a electron cloud, so you have a more easy electron tunneling, so your signal is better. So basically looking at this depends on the distance, so you can prove that you can see this is we prove only half. We didn't prove yet electron transfer from protein to protein, but we just show that we can see 1/2 side of this electron transfer. So using this method, we can understand cell death process and then oscillation of electron in living cell. Here in biology, there's definitely the cell death. During the cell death, people just look at morphology, but we see this oscillation of this fascinating electron oscillation during the cell death for this by looking at this peak, the specific peak for 520 and 550, which is here, so that you can see in necrosis. Compared to the previous hypothesis, there's no serious oscillation, but this necrosis, you can see oscillation. So you can take advantage of this real-time quantum plasmonic electron tunneling imaging method for the cell death or cell necrosis. I guess due to the time, I have to speed up something. So second line, and a heaven in the wildflower. So this is a very fascinating line that this poet predict our research. You can see like looking at heaven in the wildflower, but we see the true symmetry of flower. Then I see also the virus has a beautiful symmetry, topology, nano scale topology. This nanoscale topology allows us to create a new optical antenna. So why decorate with gold and virus? Because of the nice nanoscale topology that allow to make sensor or gene delivery system. So after we decorate, we harvest first this plant virus, and then you can decorate with gold, and you can use it in vitro diagnostic or in vivo inside of the cell. So why this is advantageous? Because of the, as I mentioned, topology of this virus. This different virus has a different topology. If you there are more hotspot, you can find out experimental data also, so that you can take advantage of importance of the nano hotspot. It's impossible to this kind of structure in 50 nanometer, but like 1 nanometer resolution of the 3-dimensional structure. So this is real data in different resonance for different. My favorite one is Bushman virus. You are eating this all the time, or cow pig mosaic virus. Obviously, you are eating this, but this doesn't really not harmful. You can take this good U virus. I named it a good virus. It's a plant virus with the decoration of the gold. You can use it as a sensor for the running resonance energy transfer or electron transfer surfacing and Raman scatter, so on. So you improve this sensitivity. The third is infinity. And to the time, I'm going to speed up fast, and I'll skip some slides. And so the third line is to encourage students. You can think about how to create many new innovative technology and also discover new science, but it's in your hand. So using our hand, and I want to encourage to you also as you are excellent students, so you can think about create many as well as technology. Why I'm showing you this computing machine? Because this very interesting history you should know. The computing machine, current situation, when I went to America, the best computer was PDP-11, but the founder of the PDP-11 was Ken Olsen. Unfortunately, he made the best computer at the time, but he said there's no reason for any individual to have a computer at his home. So he didn't have a vision. So he lost the chance to, a home computer better than Apple, because he made the best computer at the time, but he didn't see the reason that why we need a computer in a home. Anyway, so this is a history. It took a long time, but now we made solid state of the integrated circuit. Why I'm showing you this integrated circuit? Because a lot of people were skeptical about this solid state silicon integrated circuit. Why was it skeptical? Because the Wolfgang Pauli, who is one of the quantum mechanics, ironically said that one should work on semiconductor. That's the filthy mess. He didn't even believe that semiconductor is useful. So he even questioned that who knows whether any semiconductors exist. He didn't even consider that semiconductor exists. But however, the Michael Faraday, even 1833, was studying semiconductor effect. But from 1833 to 1958, semiconductor industry start a new rising point. These three gentlemen actually made a contribution. Not only Jack Kirby, who got Nobel Prize, but John Atala and Daewon Kang made a significant play to make MOS a field effect transistor. I don't know how many people know. Three of them should get Nobel Prize, but only Jack Kirby got Nobel Prize. Anybody know why? To the time, I will tell you that he's the only one lived long enough, so he got Nobel Prize later. But these two gentlemen died, so unfortunately, only Jack Kirby got Nobel Prize for this integrated circuit. So soft silicon with the E is basically microfluidic. So it is time to think about how to make integrated circuit for quantitative biology and precision molecular diagnostic. So you can create a soft silicon IC for quantitative biomedicine using many different circuit design, fluidic design, and combining with the optical sensor and so on. I'll skip a lot of stuff to the time. This is single cell study and single cell ion channel study. But however, this ion channel measurement, ion channel in the cell membrane is important to measure for drug discovery, but we can really think about also future quantum nanomedicine by modulating this antenna to deliver electron to change the conformation as well as local drug delivery. So many people already working on gold medal link to the heat sensitive ion channel or light sensitive ion channel and so on. So they use the magnetic particle as well as a piezo particle to open and close this ion channel. So this is a new way of delivering drugs. And then we are making the integrated microphysiological analytical platform to really form the 3D cell culture and so on. So we've been developing dynamic cell culture system to make organ on a chip, but the idea is we want to really show physiologically relevant dynamic 3D cell culture. Historically, Petri this is invention, the dish, and then use this cell culture dish to take advantage of the bacteriology. So his boss get Nobel Prize, but Petri is famous for the Petri dish. So this is really good for bacterial cell culture, but in human, we have to think about whether this is best for our cell culture because it's static. But we need to think about dynamic cell culture using new fluidic circuit. The reason is our body has a circulatory flow as well as an interstitial flow. So we have to develop a new microfluidic chip that allow to make a physiologically relevant microenvironment so that we can control the flow of the blood as well as the interstitial flow so that we can make real recapitulation of our body. So we developed this kind of cell culture chip before so that we can have a 10 by 10 array. And this is very important for precision stem cell biology. And let me skip some of this. I'll need to finish. And this is the cardiac chip so that you can observe how we can form IPS-based cardiac system on a chip so that we can take advantage of this to do drug screening. Okay, so you can monitor and capture in vivo-like system. We can understand the dosage dependent of different drugs of the cardiac system, or we did mini brain. So you can really mimic the brain. Currently, this is a mini brain organoid, but then this current method is fantastic to demonstrate this brain, but it is all different stage. So we realized that we need to really avoid this problem and limitation of this current technology. The solution is, instead of having all different sizes and stage of this development stage, we can form identical and similar uniform size, so that we develop this chip and to make a nice precision channel, and then with the simulations, and then we put also EEG. Otherwise, current method, you cannot really monitor this brain wave in the bioreactor. So you form these repeatable formations, and I'll skip this some of the detail, but what I like to share is electrophysiological expression can be measured by this EEG electrode, and you can see the normal brain, and this is case with the inflammation, LPS treated, so that you can see the beta and gamma wave change. And then if you also put the PTG, you can have the induced epileptic behavior, so that you can always monitor in real-time electrophysiology. And then we can think about how to really develop a new system that we can also deliver exosome to really see whether it's a treatment or not. Here, the reason why I'm just showing, reminding you this nanocrescent is we can grow together, and then you can monitor or you can modulate this system with the brain with using nanocrescent structure to see and monitor, not only seeing the electron transfer, but also modulation of the specific receptor. So we can think about the whole different microphysiological system with a different organ. The last line, in 2 minutes, I will finish this. Eternity in an hour. So this is very scary, but people can die in an hour if we don't know exactly what is the cause of this infectious disease, some case for children or even for adults. So we have to think about what is the best way to detect really fast, even for the COVID, to really treat with the right the drug. So we come out with the ultra-fast photonic PCR. So we've been working on this last 6-7 years, but we get inspiration from quantum heat engine in nature because we can use the light to speed up the gene amplification. Most of cases they use a heat block, but you can use the light to make very fast, ultra fast photothermal heating and cooling using nanoplasmonic optical antenna. So here is the idea that is a plasmonic nanoparticle that you can heat it up, cool it down really fast, and using simple LED, so you can make 30 cycle in few minutes. So you can take advantage of this kind of system where it's a different design, but basically similar concept with the nanoplasmonic PCR can be done so that we can really demonstrate rapid detection of the MERS-CoV. So this is the result that we can really capture PCR, rapid, accurate PCR using this system. So I hope I give you the big picture that having more smart mobile system can really generate a new way of capturing molecular information. Not only our body, but also you can capture information of the agricultural product or food or our aging process or environmental and so on. So we can take advantage of this smart circuit, and we can really make more accurate molecular diagnostic. So understanding quantum biology or quantum plasmonic can enhance more fast and more efficient molecular diagnostic system. Due to the time, I'm going to skip this exosome detection via ultra fast isolation system, but hopefully next time I'll come out with time to explain Exodus. But I will finish with here that even this exosome can really use this plasmonic optical antenna to detect advantage of detecting proteins as well as RNA and DNA. In summary, the successful case of all this is due to the convergence and multidisciplinary teamwork. And you really need a humble spirit, otherwise it won't work. So we need to think about also precision spirit with the microfabrication or nanofabrication. And we have to think about innovative design with a creative spirit. And we have to really make a standardization with a prospective spirit. So I'll finish with the last slide that for the Korean student, 백문이 불여일견이요. 백견이 불여일각이고 백견이 불여일행. So one picture worth 1,000 words, an understanding worth 1,000 pictures. We have to understand, but we have to really act on. So last important part is one action is worth 1,000 understandings. So not only we need to understand with a really deep insight, but we have to really make it work. So thank you very much for your attention.
Thank you for your nice talk. It was really inspiring, and yeah, it was really great. I really thank you for this nice talk. Because of time, a limited time, we may have like one question from the students. Yeah, if there's no, I can. May I ask one question for you?
Sure.
So I found the integration of like nanophotonics and biology really interesting, like using the nanophotonic the gold antenna, and the you already showed us about the comparison between the FAT technology, like the using the dye molecule to like do the like biological analysis, but can you use this nano antenna to do similar thing like the donor and acceptor of the the bioreaction as a
you can do that, but for the donor acceptor case, you can use many other like GFP or any other fluorescent molecule. The PRED advantage of PRED is you read a fingerprint. The FRED fluorescent resonance energy transfer can read only distance. You cannot really read out any specific fingerprint of the molecule.
Fingerprint mean you like line widths or the wavelengths, so things like that.
Fingerprint is like the absorption peak or vibrational peak of the molecule.
I see. Yeah, thank you. So because of limited time, let's thank to the speaker and let's move on to the next speaker. Thank you.
Thank you.
So next speaker is Dr. Hee-kyung Park. Is she here? Hello.
Yes, hello.
So she's working at Harvard University as well, and she will talk about ultra-sensitive and selective biomolecular detection using MOS2 nanolink biofats.
Yeah. Can I start now?
Yes, go ahead.
Start now? Okay. Okay. Thank you for giving me a great honor to present here. I am Hee-kyung Park in Harvard University. Now I just started the postdoc work in Harvard University, so I want to talk about one of my PhD research work about the biosensor. The name is ultrasensitive and selective biomolecular detection using the molybdenum disulfide nanolink field effect transistor. Yeah. First, I want to go briefly introduce about the advantage of 2D nanomaterial for biomedical and healthcare application, and introduce the structural engineering of 2D material. And I will go on my research about the nanoscale patterning of molybdenum disulfide using black polymer lithography and the biomolecular detection using the nanoring MOS2 bio-FET. Nowadays, the 2D material are actually utilized for the biosensor and healthcare biometrics. For in vitro diagnosis, 2D material are utilized as the building material of the bio-FET and electrochemical sensors by benefits from their high sensitivity based on their ultra-thin thickness and right surface area, and also the high flexibility and high transparency of 2D material can allow the utilizing of 2D material for the implanted in vivo monitoring sensor and wearable sensor also. And the many advantages of 2D material are reported from many papers, and 2D material are successfully used for many different kinds of biosensor. But in this talk, I want to introduce the most interesting factor of 2D material, that is the tunable material property by controlling the structural engineering method. Many structural engineering methods are reported to change the material property for various applications. The engineering method can effectively tune the optical or the electrical and chemical and thermal characteristics of 2D material, the material for electronics and sensors and actuators, and also the catalytic applications. So among them, today I want to introduce the nanoscale patterning method. Here, for example, people made the graphene like the graphene ribbon and graphene nanomesh structure to change the band structure of the graphene. So it makes the graphene, it changed the graphene band structure, it opened the graphene band structure. And also it changed the electrical property, making the on-off ratio, and changed the thermoelectrical property, and so on. And also they tried the nanomesh structure on silicon, and they get the changing of the band gap from indirect to direct, so they can obtain the different optical property on the silicon nanomesh structure. And also layer by layer seeding method can give the controllable layer thickness on 2D material, and the localized thermal phase transition under the electrode able to change the electrical junction from Schottky to ohmic contact, and the thermomechanical indentation, adding the special function for 2D material, like for the barcode application, something like that. This kind of research is very interesting, and it shows the nanostructure patterning is the very promising platform to control the material property. But conventionally, we usually use the electron beam lithography to pattern the 2D material for nanometer scale. But that process required high cost and high vacuum condition and compact operation process, and also even provide the low throughput. So in this work, I want to use another patterning method of the black polymer lithography. The black polymer is the polymer compressing more than one chemical distance monomer. The number of distance monomer determine the molecular architecture of the black polymer. So controlling the volume fraction or the number of monomer in black polymer, we can get different kind of periodic structure like cylindrical and lamellar and geological and xyloid structure. The black polymer pattern is self-organized under the equilibrium condition. The thermodynamic force is the driving force for the microphase separation between two monomers. but the thermodynamic force is counterbalanced from entropic force from the covalent linkage from the two monomers. So the counterbalance between two forces can provide the periodic nanostructure like this cylindrical or lamellar and gyroid structure. So in my work, I want to use the black polymer lithography for patterning the 2D material, the representative 2D material molybdenum disulfide. So black polymer was used as a pattern mask for lithography, and molybdenum disulfide was etched by two steps using the dry etching and wet etching process. So using the STEM study, we can get the periodic hexagonal packed nanostructure, nano hole on the MOS2 structure like this. The square diameter of the hexagonal pack and hexagonal hole structure show high periodicity, which was confirmed by the intensity profile and also FFT pattern. This kind of black polymer nanopattern method can be used on various thickness of 2D material from monolayer to multilayer. On my experience, more than 30 nanometer of molybdenum disulfide are effectively patterned by using this method. And also the interesting thing is we can get the different structure of nanohole on the MOS2, like the circular and hexagonal and triangle structure. The different hole shape on the MOS2 can be obtained by controlling the etch structure of nano holes on MOS2. It's basically the MOS2 can have different two kind of etch structure, like the zigzag and armature structure. The random structure combining of zigzag and armature structure, we can get the hexagon. We can get the circular structure. But if we change or etch to zigzag structure, we can get the hexagonal structure on AA prime molybdenum disulfide and triangle structure on AB stacking molybdenum disulfide. Actually, this study is beyond the scope of this conference, but we are trying to find the reason of this phenomena, and we are finding the differences of electrical and optical property of this structure. In this work, we want to use the nanopattern MOS2 for ultra-sensitive bio-FET. Basically, MOS2 have no dangling bond on their surface, so that it has a limit to utilize as a bio-FET without the grafting layer. But the grafting layer, like the hafnium oxide and aluminum oxide, separate the distance between the molybdenum disulfide channel and the biomolecule, and also make the unnecessary parasitic coupling between the two layers. So it results in the sensitivity and the reliability loss. So here we fabricate this kind of nano ring MOS2 structure like this. The biomolecular are selectively bound around the MOS2 nanoring edge and making the biomolecular nanoring edge on the MOS2 surface. This figure shows the SEM image of the fabricated nanoring molybdenum disulfide channel having the periodic nano rings have the average diameter of 23 nanometer size nanoholes. And we measure the electrical property of this device. It shows the excellent N-type property with the on-off ratio of 10/4. And the field effect mobility is 6.5, average field effect mobility is 6.5 centimeters square per volt second. But the large substrate swing and the Schottky junction was confirmed in that device. So we thought that the exposed nanoring edge on the MOS2 resulted in a little degradation of the electrical property of the MOS2 FET. And this figure is our experimental concept. We want to introduce the nanoring selective chemical functionalization using the nanoring at this abundant dangling bond. So we selectively replace the nanoring at the sulfur to oxygen atom and process the surface functionalization using the APTS and glutaraldate process. And to detect the target biomolecular cortisol, we use the aptamer. In this work, we significantly reduce the distance between the biomolecule and molybdenum disulfide by using the nanoring selective chemical functionalization and also using the aptamer. That size is very smaller than the antibody. And also the rich nanoring edge area on the nanoprot MOS2 surface induce the huge number of binding of the biomolecules, so which can excellently amplify the carrier modulation of biliary on the MOS2 channel. For the nanoring edge selective chemical bonding, we have to replace the edge exposed sulfur atom to oxygen atom. We found the optimized oxygen treatment condition that only oxide the edge atom, not on the molybdenum and sulfur atom on the MOS2 bezel plane. So we confirm the edge selective oxidation using the XPS study. So on the nanoring MOS2 case, oxygen treatment reduce. We can see the oxygen treatment reduce the ratio between the MO and sulfur atom from 2 to 1.87. It means the sulfur atom having a low binding bond at the end, H was replaced to oxygen. But otherwise, on the pristine MOS2, we cannot see the reduction of the ratio between the MO and sulfur atom. And we confirm the nanoring selective chemical bonding using the gold nanoparticle tethering experiment here. Showing in this inset figure, we can see the gold nanoparticle were attached around the nanoring structure, not on the MOS2 bezel plane. So the binding efficiency of the gold nanoparticle was confirmed by collecting the gold nanoparticle number. So we can find the gold nanoparticle number is increased more than 10 times per micrometer scale compared with the pristine molybdenum disulfide. Using the nanoring MOS2 bio-FET, we measured the sensing signal of the cortisol biomolecule by injecting the different cortisol concentration from 1 attogram per milliliter to 1 microgram per milliliter. As shown in this figure, we can see the increasing concentration of cortisol makes the decrease of the current level. This is because the negative charges cortisol attached at the nanoring edge structure increase the energy barrier of the nanoring, and it hinders the electron pass on the nanoprot MOS2 film channel. And also we compared with this sensing property with the pristine MOS2 here. Basically, on the pristine MOS2 have less dangling bond on their surface, so they cannot provide the molecular binding site on their surface. So they result in the bad detection limit of almost 1 nanogram per milliliter. But otherwise, the nanoring MOS2 FET shows the great S shape with the detection range from 1 attogram per milliliter to 1 picogram per milliliter, and a low detection limit of 1 attogram per milliliter. This result verified the effective functionalization of biomolecule on the rich non-ring edge on the MS2. And we also confirmed the selectivity and the clinical applicability using these two tests. Here, compared with the antigen, the steroid hormone like the progesterone and aldosterone shows a little change, but it's smaller than the variation in the cortisol. But we thought that this is because of the chemical structure similarity of these two hormones with the cortisol. And also we tested the detection under human serum and the artificial saliva here, and sensitivity was decreased compared to the result at KVS, but it shows the similar detection limit at 1 attogram per milliliter. Yeah. In summary, in this talk, we introduced the nanoscale patterning of 2D material using the black polymer lithography. We get the ultra-high sensitivity of the ultra-low detection of limit of 1 attogram per milliliter, and we get excellent selectivity and clinical applicability by testing the selectivity test and the measurement under the artificial saliva and real human serum condition. And we believe this kind of structural engineering method to make the MOS2 non-ring edge-based bioFET would provide a promising platform for everyday biosensor with extraordinary sensitivity and selectivity. Yeah, thank you for your attention. Yeah.
Thank you for your talk. We have 3 minutes left, so we can take some questions from the audience. If there's any question, you can leave chat or just raise your hands and speak out, please. Yeah, I always find the audience always needs some time to digest your talk. So let me make your question. There's one question actually. Please go ahead.
Thank you for your meaningful presentation. I want to ask one question. How can these systems achieve high sensitivity between similar biomaterials?
Can you tell me again? I didn't hear clearly. Yeah.
How can this device achieve high sensitivity between similar biomaterials?
Similar biomaterial. Similar biomaterial means
such as steroid. Yeah, you told between next slide.
Yeah.
Next. Maybe, next one. Yeah, here, yeah. How can we get selectivity in this device?
Because I use the cortisol for detection. I use the aptamer for fabricate to detect the cortisol. So I use that one. That's why my device show high selectivity to the cortisol biomolecule. But actually, the chemical structure similarity of the progesterone and aldosterone. So that's why we get the little increase in the current behavior like this. Yeah.
Thank you.
Yeah, is there more questions? I have a question about the fabrication process. So when you see the picture of the sample, the orientation is kind of looking like it's changing over the area. So why is it? And could you control that?
Actually,
so if you look at the like large area,
you mean the controlling about the edge structure?
Like in the largest scale, the orientation of the kind of the hexagonal or this honeycomb shape, that orientation is looking changed.
Right. Actually, the dry etching condition cannot control the shape of the structure, but actually wet etching condition is anisotropic etch, the MOS2. So using the wet etching process, we can control the etch structure like this. Yeah.
I see. Thank you. So yeah, due to the time, let's wrap up the first session of the symposium. We will have break until 10:40, and we will come back at 10:40. Thank you. Thank you for all the presenter for this session, and thank you for the audience. Thank you.
Start your journey with the best fruit and vegetable product on the market by going to balanceofnature.com and use discount code Fox News.
Friday, Lee Bryce. Part of our Can't Miss All-American Summer Concert Series, presented by Best Western Hotels and Resorts.
Great, so it's done.
When you need a reliable and professional plumber, a sewer technician who can handle tough jobs, a cooling expert to work on your AC, or a technician that can handle anything, just call ABC. No matter what your home needs, we have the expertise to do the job once and do it right. Just call ABC and consider it done.
Digital marketing has changed the way businesses reach their customers. It's crucial to their success.
AmericanEagle.com builds dynamic, data-driven, multi-channel digital marketing programs. From SEO and email marketing to online advertising campaigns, converting leads into sales by optimizing your digital investment.
Is digital marketing driving your sales?
AmericanEagle.com, building your digital mindset.
President Biden's undeniable dereliction of duty in Afghanistan, even some of the media mob, they're being forced to face reality. That's not stopping some Democrats from trying to claim he's actually doing a great job. For example, embattled Governor Gavin Newsom said Monday he's incredibly proud of President Biden. Speaker Pelosi even had the audacity to claim that Biden's withdrawal was strong and decisive. Nancy, sell that line of Adam Schiff to any of the thousands of Americans behind enemy lines in Afghanistan tonight that we can't protect because of Biden's decisive action. Here for reaction, author of the huge bestseller, now almost 1 million copies sold, #1 as of today for the 5th consecutive week, #1 on Amazon.com for the 5th, well, actually 6th consecutive week. I know this isn't about American Marxism. He's also the host of Life, Liberty, and Levin. Mark Levin, I never imagined we would be seeing this in our lifetime. Americans caught behind enemy lines. We had all the time.
some material related. Good morning. This is a short talk you asked me to give about some material. Good morning.